Hello, good people. Welcome to video number 1 of topic 6.4. Now, 6.4 talks about definite integrals as accumulators, and it coincides with the idea of the fundamental theorem of calculus that we talked about in 6.7. So, just some big ideas that you might run into as we start to do more and more free response practice. You're going to find that the AP exam often gives a rate or a definite integral function and ask you to find the total amount or a function value. So whenever they give you a rate and they want you to find the total amount, whenever they give you a rate and they want you to find a function value, that should be a clue to us that we need to take a definite integral. Or if they just outright give you a definite integral, then you should know that we need to use the idea of accumulation as a way to figure out the answer. So this idea is called accumulation, and it's based off of the fundamental theorem of calculus, FTOC, the fundamental theorem of calculus, which we just talked about in topic 6.7. And these problems occur in many different formats. You're going to see these problems in word situations, wordier problems. You might see them in terms of motion graphs or motion equations. You might see them just given in terms of graphs or equations. So they definitely are not a specific representation. They occur in all types of representation. But here's the deal. The problem gives you a derivative, which is a rate, and it asks for a definite integral, which is the value. And so that's how you know that you're going to need to apply the fundamental theorem and the idea of accumulation to these types of problems. Now, in the previous video, we talked about the fundamental theorem of calculus being a way to find the exact area under the curve, right? But what if we take this part of the fundamental theorem of calculus and shift it to the other side? What if we add this f of a on both sides of the equal sign? Well, then that's how we can get this setup. Now, if you look at this setup, some people call this the accumulation model because it's telling you if you want to find a final amount, which is what some of these questions are asking you to find. If you want to find the final amount, it's equal to the initial amount plus the net change in that amount based off of the integral of the rate of that amount. Okay, that's a lot of things to say. But you might recall that earlier we said a definite integral finds the total amount or the net change, right? The net, excuse me, the difference in the amount. Well, if this is going to find how much the original quantity has changed in this time period from A to B, and if I know how much was there at the beginning, then if I add it on, it's going to give me how much there is at the end. And so this setup is based off of the fundamental theorem, right? The fundamental theorem says the difference between the original function evaluated at the endpoints is equal to the difference of the endpoints is a way to figure out the definite integral. Well, this says, well, what if we add the initial amount to the other side? Then we're going to have initial amount plus the definite integral, which tells me how much it's changed in that interval. Well, then that's going to give me the final amount. And that's the big idea that, and the most, I guess, useful idea of the fundamental theorem of calculus. Fundamental theorem of calculus is a pretty overwhelming idea in that, think about what it tells us. To find a definite integral, I need to know the relationship between a function and its derivative, right? So this kind of combines both ideas of an integral as finding the area under the curve and the idea of the derivative, knowing how to find a derivative, or more importantly, an antiderivative. We can combine both sides of calculus and in one formula use both. Okay, so We can see these problems appear in different ways. So here's one way we can appear. Let's say you're given a derivative, right? So you're given the actual derivative equation. If f of 5 is 9, then can you find f of 8? At the beginning, you're thinking, well, in order to find f of 8, I need to know what the original function is, but I don't know what the original function is whose derivative is this complicated looking thing. Well, that's okay, because if you think of the fundamental theorem, the fundamental theorem says if you evaluate an integral from 5 to 8 of f prime, that's going to equal the original function f evaluated at 8 minus the original function f evaluated at 5. Oh, but we know what f of 5 is. F of 5 is 9. So I can replace this with 9. And if I'm trying to figure out f of 8, I can just add this over. So I'm basically using this accumulation model to figure that out, right? So another way I could write this is f of 8 is equal to f of 5, which is the starting value, plus the integral from 5 to 8 of the function f prime. Well, we know what f of 5 is. We know that that's 9. Plus, we don't know what this is. However, we do know that there is a calculator feature that allows us to use definite integrals. And so we're going to use that to figure that out. So our function here is sine squared of 3x minus 7. So I'm going to go to my calculator. And if you forgot, or if we haven't done this before, and I forgot maybe, let's find the definite integral feature on the calculator. We know there's a derivative feature, but there's also a definite integral feature. So I'm going to go to math, and option number 9, right below the numerical derivative, option number 9, way down here. You don't have to go all the way to the bottom. You can just press 9. It's going to set up a definite integral format for you, and you just fill in what you need, right? So I'm going to choose 9, and it creates this. Well, we are going from 5 to 8 of the function. Now, wait, what was the function? Sine of 3x minus 7. Now, I'm going to need to close this, and then I'm going to need to square it. So the calculator reads this as this whole thing close all of this thing squared, not just the inside squared, but the whole thing. That's the way the calculator reads it. Normally, we put the 2 here, but the calculator, in calculator language, if you will, you can put it there. If you want to make sure that it's in the right place, you can also put parentheses around everything and say, oh, I'm taking the whole sine 3x minus 7 and squaring it. And I'm going to come over here, and then we have to declare what the variable of integration is. Well, we're putting things in terms of x. So this should match what we're trying to find here, which is this, right? Okay, let's go back, press enter, and here's our answer. Oh, I forgot to check something, and I can see it right now that I made a mistake. When I pressed enter, the calculator evaluated this in terms of degree. But remember that in calculus, all arbitrary functions are based off of radian. So I need to go back to mode. I need to change it back to radian. And now, when I do the definite integral, I should get the correct answer. I'm going to go up, press enter, and this is the correct answer. 1.43. Let's do 4 decimal places, and that way our answer will be accurate up to 3 decimal places. So we're going to go an extra decimal place when we're doing the work so that our final answer will be correct up to 3 decimal places, which is required by the exam. 1.4319. 4319. 1.4319. And when I put those two together, I'll get 10.4319. And I'm going to say this is an about, because I did cut it off, right? I did cut off my decimal. So we're going to say it's about this. But I figured out the answer. I was trying to find the value of f of 8 without knowing what f is. By using the fundamental theorem of calculus and the accumulation model, I can figure that out. Okay, let's try another one. This is going to be a little bit different because we're looking for f of 1. Well, if I take the integral from 1 to 5. Now, why am I putting the 1 on the bottom and the 5 on top? Over here, I put the 5 on the bottom and the 8 on top. Why am I doing that? I'm trying to go from the lower, smaller value to the upper, larger value. I'm trying to set up a quote-unquote correct integral. So if I set up this integral, this is going to give me f of 5 minus f of 1. Now, here, I'm not looking for the initial. I'm not given the initial. I'm given the ending, the final amount. And so I'm going to add this over to this side, and I'm going to subtract this over to the other side, right? Because I know f of 5, they give it to me, and I can figure out this. So I need these on the same side, but this f of 1 has a minus sign in front of it, so I'm going to add it over. So I'm going to say f of 1, and then it's on the same side as this, but I'm going to subtract this to the other side. And I'm going to get this. Cool. Well, we know f of 5 is 9 minus. I'm going to need to evaluate this function. And so here I start to realize, hey, I'm going to need to use this function equation several times. So why don't I just save it in y1? And I don't have to retype it every time. And I can save it in y1 by doing this. Sine of 3x minus 7 squared. Now it's saved in y1. So when I come back over here, I'm going to do a definite integral. I'm going to go to math. Option number 9 on the bottom, the function integration is what I need. This time we're going from 1 to 5. And so that I don't have to write the equation all over again, I'm just going to say, hey, remember what I saved in y1 calculator? And so I'm going to go alpha trace. It gives me all the y equations that are saved. Y saved mine in y1, so I'm going to press 1. And then that'll be x. So if I have to use the same function multiple times, it might be a good idea to just save it and then use the shortcut name of where you saved it to figure that out. When I do this, I get an answer, 1.9415. 1.9415, but I'm subtracting this, right? So when I do the subtraction, it'll be 9 minus whatever answer I got here, and that's going to give me about 7.058. 7.058. So it's about 7.058. And that's it. I figured out my f of 1 value. We're going to come back and we'll do some more examples in practicing this new interpretation of the fundamental theorem of calculus. This is called the accumulation model. Again, you're going to see problems where they're going to ask you for the final amount. They give you the initial amount and they give you the rate of change. So if you take the integral of the rate of change, that's going to be how much it's changed, how much the original amount has changed in that time interval, added to the initial amount, and that's going to give you the final amount.